Okay, so this is an inelastic collision problem involving an explosion. So we initially have our launcher and satellite, and the best way to separate these things when they're in space is by exploding bolts. And so an exploding bolt then can go ahead and provide some energy to move those objects apart. Okay, so if we want to figure out what we're given, then we're given the launcher's velocity, and we want to find out in the first part of the question, what is the satellite's velocity? Okay, so first of all, we start with our launcher and satellite at rest. Okay, and conservation of momentum tells us our initial momentum equals our final momentum. Now, initial momentum here is 0. Okay? So our initial momentum is 0 because everything's at rest. And that has to equal our final momentum. Momentum, remember, is mass times velocity. Okay? So our final momentum is the mass of the launcher times the launcher's velocity plus the satellite's mass times the satellite's velocity. So therefore, the satellite's velocity, once you solve this algebraically, you have to subtract this from both sides, then divide by the satellite's mass. You get negative mass of the launcher, velocity of the launcher, divided by mass of the satellite. So we plug these numbers in that we're given. The launcher mass is 1,500 kilograms. And the launcher moves away at 2.25 meters per second, divided by the satellite mass, which is 4,800 kilograms. Okay. Now, you solve this here. And what you find is that the satellite velocity is negative 0.703 meters per second. Okay? So the negative sign tells us it's moving in the opposite direction of the launcher. So if the launcher is moving this way at 2.25 meters per second, the satellite then is moving that way at 0.7 meters per second. So the minus sign is just telling us it's in the opposite direction of the launcher. Okay? So there's the answer to part A. In part B, we are asked to calculate how much kinetic energy has changed after this explosion occurs. So I'm going to go ahead and erase this, and we'll put the answer up here. So let's erase this. And the satellite's velocity that we solved was negative 0.703 meters per second from part A. Now, part B, we want to figure out how kinetic energy has changed. Well, the initial kinetic energy, well, it's at rest, so our initial kinetic energy was 0. So the kinetic energy then has changed. The change in kinetic energy is given by our final kinetic energy, which is 1/2 mass of the launcher times its velocity squared, plus the kinetic energy of the satellite, which is 1/2 times its mass times its velocity squared. So we plug these numbers in. Mass of the launcher, again, is 1,500 kilograms. And its velocity was 2.25 meters per second. Plus the same for the satellite. Mass was 4,800. And the satellite's velocity, we found, was negative 0.703. And that has to be squared. Okay, you do this calculation here. And really, it's very easy to forget the squared part here. So don't forget the squared when we're dealing with the kinetic energy. The answer you get here is 4980 joules. Okay? So, so this explosion added just about 5,000 joules to the system's kinetic energy. Okay, and really with this explosion, most of that energy that's released goes into heat. But some small fraction actually does go into actually moving the objects into the kinetic energy of motion. But again, most of it is heat that's released here.